Hey, physics class. This lecture is on momentum, which is when object A hits object B. And I have to be honest, this is a big old lecture. So go get yourself a cup of coffee, come back, sit down, and get ready. It's going to take a minute. Oops. All right, so what's momentum? Momentum is inertia in motion. We have the mass, which is inertia, and we have velocity. So something that's a large barge would have a lot of momentum, or something that has a large velocity, like a bullet down here, has a lot of momentum. Okay. So if I have a truck and a skateboarder going the exact same speed, which has the most momentum? All right, which also has the greater inertia. All right, the truck has the greater inertia, it's got more mass, and the truck has more momentum probably, definitely if they're going the same speed, definitely if they're going the same speed, it's going to have more momentum. All right, now the truck is stopped and the skateboarder's moving. All right, so which has the greater momentum? The skateboarder has a greater momentum since the velocity of the truck is 0, but the truck still has greater inertia, which it has more mass no matter what. All right, can you think of a case where the truck and the skateboarder would have the exact same momentum? All right, and think about the formula, what you'd have to do to get them to come out the same. Okay, if the skateboarder was going much faster than the truck, then they could have the same momentum, but he'd have to be like unrealistically that much faster. All right. So for example, you have a 10,000 kilogram truck has a velocity of 1 meter per second. What would the speed of a 50 kilogram skateboarder need to be to have the exact same momentum? And if they have the exact same momentum, if they crash head on, then the overall result would be that they would stop. Okay, so you're gonna have to think about there's gonna be a lot of velocity involved in that skateboarder. So here's your formula: momentum equals mass times velocity. And you would just plug in, go ahead and see what you could do. Get your calculators, all right? And the skateboarder would have to be going 200 meters every second. That's ridiculously fast, right? 200 meters in a second. But that would equal out, and if a skateboarder did go that fast and it crashed into a truck, the truck would stop. All right, so remember, force was mass times acceleration, momentum's mass times velocity. Those two things are obviously related in a way. So when we look at stopping an object with momentum, we have to apply a force, right? And we're going to then cause acceleration. We're going to stop it. And note that the changing object's momentum depends on the force and the amount of time it takes. Okay. What we call that when we change momentum, we give it a new word, we call it impulse. An impulse is an object, the impulse is equal to the change of the object's momentum over a period of time. All right, so we're going to change usually it's the velocity we're changing, right? And it's almost never the mass we change. We're going to look at a change in velocity, right? And if you think about a change in velocity and you think about a change in velocity over a certain amount of time, you start thinking about acceleration. So acceleration is change in velocity over a certain amount of time, okay? And force is mass times acceleration. So when we start to look at this, we can plug in and we could say force is mass times the change in the velocity over the time, right? We can plug that in for acceleration, okay? And multiply both sides times delta t, right? And you'll end up getting the equation for your impulse. So a force applied over a time results in a change of the object's momentum. So let's think about this. I think I have you guys do this just to torture you for fun. But if you jump and you don't bend your knees, it kind of hurts. And if you jump and you bend your knees, you've extended the amount of time it takes for you to slow down. And it doesn't hurt as much, all right? That's why you should always bend your knees when you land, all right? Think about throwing an egg. You're not writing this down because it's in red-ish orange. You throw an egg or something at something that's soft and catches it, a sheet or something that's soft and catches it. It's a long period of time to slow it down, so it's a small force. I'm so ignoring this. Just keep going in life. And if it hits a wall, then the egg hits it. It's a very short period of time for it to change the velocity, change the direction, accelerate it. And so the egg will crack. It's a larger impact of impulse. Okay, so increasing momentum. To increase an object's momentum, we apply a greater force for as long as possible. All right. So how do we apply that? Well, if you're striking a baseball with a bat, you want to apply a large force for as long as possible. All right, and then they're going to talk about, well, we usually do an average force because the force is going to vary slightly through that application. So we won't do any complicated calculations with that. All right, decreasing momentum. Here's a question for you. If you're driving along, would you rather hit a brick wall or a haystack? And I think we all know the answers. You don't want to stop suddenly. You don't want to change your velocity suddenly. Since the change in momentum is the same, you're going to go to zero. The impulse applied is the same. What we want to do is we want to minimize the force and lengthen the amount of time. So we want to increase the amount of time, decrease the force. That'll make the impact much nicer. If you hit a brick wall, you have a very large force for a very short period of time. Just bam, you hit it, you're done, right? But you have a haystack and you can just slowly slow down and that decreases the force. That's better for your car and your neck and everything else. So automobile safety has taken that and they have things that slow you down. Airbags slow you down gently over a larger time. Crumple zones are designed, it might destroy your car, but it slows the impact down. Instead of just stopping, it crumples it, which gives you a longer time before you stop. I always wish that they would have applied this to football helmets, which are very hard on the outside, and they stop the impact very fast. If you would do a softer thing on the outside, you would have more time, less force. Okay, so let's do some fun math. So you have an average force here, 2,200 kilogram vehicle is traveling at 26 meters per second. It can be stopped in 21 seconds with gentle brakes. So go ahead and do the math there. 3.8 seconds if you slam on the brakes, or 0.22 seconds if you hit a brick wall. What is the force exerted on each of these? All right. So we have force, we have the time. I've given you the time. And you have the mass, right? So when you do the math, it'll be 21 seconds will give you a force of negative 2.7 because it's slowing you down, right? That's the negative, times 10 to the 3 newtons. I'll get my voicemail later. And then 3.8 if you slam on the brakes, 10 to the 4th newtons. And if you hit a brick wall, you're at 10 to the 5 newtons. And now we're talking bad, all right? This obviously much, much worse by exponentially. Okay, conservation of momentum. The momentum before a collision has to equal the momentum after a collision. So if you have two things hit each other, whatever their combined momentum is before the collision has to be the same as after the collision, right? Conservation of momentum, again, before the collision has to be the same as after the collision. So we can just use that to do some math, basically, which is if you add up all of your momentum, and this is all before collision, but the mass of the ball A and the velocity of ball A and the mass of ball B with the velocity of ball B before the collision has to equal the mass of ball A, velocity of ball A, and the mass of ball B and the velocity of ball B after the collision, right? And the subscripts is just keeping track of which balls are hitting where. So we can do that with trains. Pool table balls are always good. right? Okay, and then just some conceptual things. What's wrong with this picture? If you look about this picture and you think about it, if the fan pushes on the molecules, right, would that not push you forward? And the answer is no, because it's going to push back. This is sort of Newton's third law, right? You have an isolated system here. This works because you're actually kicking the gas out the backside. It's not an isolated system. All right. Conservation of momentum works for rockets as long as we consider it to be one system and the mass is getting kicked out the back, right? So it's like in outer space. How would you move? You would throw something and that would move you one direction. It's the same idea. All right. So whenever an objects collide in the absence of a force, the momentum is conserved. So meaning that we're not still hitting our gas and driving through it. We just have two things that are just rolling along and they hit each other. Okay, an elastic condition is going to be when the two objects basically bounce off really nicely, right? They don't stick to each other. So like clay would roll and it would kind of stick to each other or get deformed. It doesn't really work very nicely. An elastic collision, which is much nicer to do the math on, are when they really bounce off each other. Okay, inelastic collisions are when things stick to each other. We'll do the math on it as well, but it's not getting your nice bounce, right? The momentum's still conserved, but it's going to be a little different. All right. Newton's cradle is an example of an elastic collision. It would not work with clay balls, right? They nice and they bounce off each other. Okay. When you look at hitting that 8-ball, you should be thinking about a nice, crisp, elastic collision. So you don't want to strike it and just have your balls roll forward. You want a nice collision. So you're going to give it a little bit of momentum so that it bounces back. Okay. Inelastic collisions, if things stick together, if you had two trucks going together that are the same exact speed and they hit and they're the same mass, then the overall velocity would be 0, right? But if I have one truck going towards a stopped, or I guess these are train things here now. These are trucks, these are trains. Anyway, it's going this way towards B. This one has a velocity of 0. This one has 10. The combined mass and the after collision thing will have to be the velocity is 5, right? Since we have both masses going the same direction now. Okay, so just for fun, large fish swims at 3 meters per second towards a small fish and swallows it for lunch. What is the momentum before it has lunch? So you want the large fish is swimming at 3 meters per second. It's swimming towards a small fish that weighs 2 kilograms, but it's not moving. So do no velocity here. This one's supposed to be moving. This one's not moving. All right. And find the momentum here. And then figure out what's the momentum. It has to be the same after lunch. So what's the velocity at the end? And so, yeah, hopefully you did that. Inelastic collision, example 2. A 1,875 kilogram car goes 23 meters per second and rear ends a 1,025 kilogram car going 17 meters per second on ice. This is a no friction example because we like to be nice. What's the speed of the two cars after the collision? Okay, so what we have is before and after, and they've stuck together. So your after is, I'm sorry, I did that too fast. Your after is 20.9 meters per second. Okay. Momentum conservation also explains recoil. When you have a cannon and it recoils, the mass and velocity of the cannon is going to equal the mass and the velocity of the cannonball. Those two will equal out. So collision in 2 or 3 dimensions, this just is the same thing, but now we're going to add in some fun vectors. If you start with a ball going this direction and we have one ball, we only have momentum in the X direction. We have 0 momentum in the Y direction, which means, oops, didn't mean to do that, which means when these balls go on their merry way into the Y direction, these two balls better equal out 0 for the y direction. Now there is momentum in the x direction, so as these go off, that momentum has to be conserved. But the y direction has to be negated down to 0. Okay, so here we go, same idea, but now we're adding our vectors. We have the vector of this one and the vector of this one, remember, and the vector of this one and the vector of this one. If we had 0y momentum, then these two, this one and this one, better equal each other, all right? And this one and this one combined have to equal whatever our initial momentum was, okay? And again, you might end up with a lot of subscripts here because we're going to have the mass of ball 1 and the velocity of ball 1 initial in the x direction, and the mass of ball 2 and the mass of ball velocity of ball 2 initial in the x direction, and then final in the x direction, final in the x direction, and we do the same thing in the y direction. So you end up with a lot of subscript, but it actually helps you kind of keep track of everything. Okay, so here we go. Particle 1 is moving at a velocity and hits particle 2 at rest. In the x direction, the initial momentum is m1v1. In the y direction, the initial momentum is 0. Okay, now we end up getting more complicated. We have, this is the same thing you saw before, but now we're adding in the angles. We have our vectors, all right? And we have theta here and we have phi here, and we just use two different symbols because we have two different angles and you got to keep track of them. So again, the same exact equation you saw before. We have 0 for the y direction because that was the initial. There was nothing in the y direction. And ignore the energy equation here, all right? Just ignore this. We're going to get to that for the next slide. Next lecture, excuse me. So, all right, next lecture we'll hit that.